Every detail in this story comes from real scientific research and observation. There is a structure in our solar system so vast, so thin, and so precisely organized that if you scaled it to the size of a piece of paper, that paper would stretch wider than a football field and yet remain exactly as thin as it already is. It exists around the sixth planet from the Sun. It has been there for tens of millions of years, possibly hundreds of millions. It is made of ice. It is made of rock. It is made of dust so fine it behaves like a fluid. And it is, by any measurement, one of the most beautiful physical structures in the known universe. Tonight, you are going inside it. Welcome to Quiet Science at Bedtime, a channel where real science becomes the landscape you fall asleep inside. This channel is still very new, and if what you hear tonight moves you, please consider subscribing, leaving a like, and turning on notifications. It genuinely helps this grow, and there is much more to come. Everything you are about to hear is grounded in real scientific data, from the Cassini spacecraft's 13 years in orbit around Saturn, from Earth-based telescopes, and from the published research of planetary scientists who have spent their careers studying the most complex ring system in the solar system. The science is real, the distances are real, the ice is real. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. Saturn is the sixth planet from the Sun, orbiting at an average distance of approximately 1.4 billion kilometers, nearly 10 times the distance between the Earth and the Sun. At that distance, sunlight takes approximately 80 minutes to arrive. The light illuminating Saturn's rings right now left the Sun 80 minutes ago. It is, in that sense, old light by the time it reaches anything out there. Saturn itself is a gas giant, a planet with no solid surface, composed primarily of hydrogen and helium, with a dense atmosphere that transitions gradually into deeper and denser layers as you descend, eventually reaching a core that may be rocky or metallic or something stranger still. The planet is approximately 120,000 kilometers in diameter, roughly 9.5 times the diameter of Earth. It rotates on its axis once every 10 hours and 33 minutes, a rotation so fast that Saturn bulges noticeably at its equator. It is visibly oblate, flattened at the poles and widened at the equator, more so than any other planet in the solar system. But the rings are the reason you are here. Saturn's ring system extends outward from the planet's equator to a distance of approximately 282,000 kilometers from the center, nearly 240,000 kilometers from the cloud tops. That is roughly the distance from Earth to the Moon. The ring system spans that distance, and yet the rings themselves are extraordinarily thin, in most regions between 10 meters and 1 kilometer thick. The main rings cover a radial distance of 70,000 kilometers, and yet their vertical extent is almost nothing. If you were to scale the main rings to the width of a piece of standard printer paper, they would be approximately 1 millimeter thick, less in most places, far less. This is where you are going tonight. Not above the rings, looking down at them the way Cassini's cameras photographed them from orbit. Not outside them, watching the sunlight scatter off the ice. Inside them, moving through them at orbital velocity, surrounded on all sides by a continuous field of particles ranging from the size of a grain of sand to the size of a house, all of it slowly, quietly orbiting Saturn in near-perfect silence. There is no sound in space, but there are electromagnetic waves, and there is data, and there is structure, and there is a kind of order in the motion of hundreds of billions of individual particles that, when you understand what governs it, becomes something very close to music. Tonight, you are in the middle of that order. You are positioned now at the outer edge of the B ring. The rings of Saturn are divided into distinct regions, lettered roughly in the order they were discovered, rather than their order from the planet. Moving outward from Saturn, the main rings are D, C, B, the Cassini division, A, then the F, G, and E rings beyond. The B ring is the brightest, the most opaque, and the most massive of all of them. It is where the density of particles is highest. It is where the ring system is most fully itself. The outer boundary of the B ring is sharply defined, one of the sharpest edges in the solar system, maintained by a gravitational resonance with Mimas, one of Saturn's inner moons. Mimas orbits Saturn once every 22.6 hours. A particle at the outer edge of the B ring would complete exactly 2 orbits for every 1 orbit of Mimas. This 1 resonance means that any particle attempting to exist just outside that boundary receives a small gravitational kick from Mimas at the same point in its orbit every single time. Over millions of years, those repeated kicks have swept the outer B ring edge clean, creating a boundary that drops from extremely high particle density to almost nothing in a distance of less than a kilometer. You are at that edge now, moving inward. The particles here at the outer B ring begin to appear around you, not as a wall you enter, but as a gradual thickening of the space you move through. First, there are occasional small particles, fragments of water ice, a few centimeters across, catching the distant sunlight at low angles. They are not traveling in a random cloud. They are orbiting. They are all moving in the same direction, prograde, the same direction Saturn rotates, at approximately 20 kilometers per second at this distance. You are moving with them. You are part of the orbital flow. Everything here is moving. Everything here has been moving for longer than the first multicellular life existed on Earth, and it moves in silence. The particle density increases as you drift inward. More fragments appear in your immediate vicinity, some tumbling slowly, some nearly still relative to your position, because you are co-moving with them in nearly the same orbit. The relative velocities between adjacent ring particles are extremely low, typically a few centimeters per second or less. When ring particles do collide, they collide gently. The collisions are almost perfectly inelastic. Energy is absorbed rather than returned, which is part of why the rings maintain their flat, planar structure rather than dispersing into a three-dimensional cloud. The collisions damp out vertical motion over time. The rings flatten themselves. You are inside a structure that is continuously self-organizing, continuously flattening, continuously redistributing energy through countless gentle collisions, maintaining a flat disk through the same physics that govern the formation of the solar system itself. The rings are, in this sense, a laboratory for planetary formation happening in slow motion. The ice surrounding you is not pure. Water ice is the dominant material. Approximately 90 to 95% of the ring particles by mass are water ice, H2O, the same molecule that makes up Earth's oceans and glaciers and snowflakes. But the remaining 5 to 10% is a mixture of silicate rock, carbon compounds, iron oxide, and trace organic materials. The contamination is what gives different ring regions their distinct colors when imaged in certain wavelengths. The B ring is relatively bright and white because it has a high ice content and because the constant gentle collisions between particles grind and refresh the surfaces, exposing fresh ice rather than the darkened, irradiated surface that accumulates over time when ice is exposed to the solar wind and cosmic rays without replenishment. The particle you are closest to right now, the one drifting perhaps 10 meters to your left, slowly rotating as it orbits, is a fragment of water ice roughly the size of a large suitcase. Its surface is slightly rough, fractured from previous collisions that were slightly less gentle than most. The fracture faces catch the light differently than the smoother original surfaces. In the low, raking sunlight at Saturn's distance, it glows a faint warm white, the color of old snow. It has been in this orbit for a very long time. How it got here is a question that has not been fully answered. The rings may have formed from the disruption of a moon perhaps similar in size to Mimas, which strayed too close to Saturn and was torn apart by tidal forces, or was shattered in a collision with a comet or asteroid. Or the rings may be primordial, assembled from material that never coalesced into a moon during Saturn's formation. The Cassini mission produced evidence suggesting the rings are geologically young, perhaps only 10 to 100 million years old, which would make them a relatively recent feature of the Saturn system, forming around the time of the dinosaurs on Earth. But the debate continues, and the particle beside you carries no record of its own origin. It simply orbits, as it has always orbited, as it will continue to orbit until something changes. The light here is unlike anything in Earth experience. Saturn is approximately 10 times farther from the Sun than Earth is. The inverse square law of light intensity means that the sunlight here is approximately 100 times dimmer than it is at Earth's distance. This is not darkness, it is a soft, golden, perpetual late afternoon light, the kind that arrives at a low angle and makes everything glow rather than illuminate. Every ice particle catches this light on its sun-facing side and reflects it, the cumulative effect, billions of particles, all reflecting, is what makes Saturn's rings visible from Earth as a bright band, even though no individual particle could be seen by any Earth-based telescope. From inside, the effect is different. You are not looking at the rings from outside. You are inside the reflective medium. The light scatters in every direction around you. The particles near you glow from multiple angles as light bounces between them. The ring plane extends outward in every direction to distances far beyond what you could see, even if the view weren't obscured by the particles themselves. Above you and below you, the ring is only a few hundred meters thick. Beyond that vertical extent, there is open space, the blackness of the outer solar system, punctuated by stars that are dimmer here than they are from Earth. You are inside a structure that is simultaneously enormous and impossibly thin, simultaneously ancient and temporary, simultaneously chaotic and perfectly ordered. It is one of the strangest places in the solar system, and it is very, very quiet. In, out. Let that quiet settle now. The orbit is holding you. The physics is holding everything. The B ring has structure within it that is only visible from close range. The large-scale rings, the A, B, C rings, visible from Earth, are themselves composed of thousands of individual narrow ringlets, each slightly different in density, composition, and orbital properties. The B ring alone contains hundreds of these substructures, some sharply defined, some gradual. They appear as alternating bright and dark bands when imaged radially from outside, but from inside, moving through them, They manifest as gradual changes in particle density, regions where you are surrounded by fewer particles, more sparsely spaced, and regions where they crowd more thickly. Some of these structures are driven by gravitational resonances with Saturn's moons. Others appear to be self-organized, density waves that arise from the collective gravitational interactions of the ring particles themselves, analogous to the spiral density waves that organize the arms of galaxies, but operating on a scale of kilometers rather than thousands of light years. You are now drifting through a density wave. The particle spacing is decreasing, more fragments per cubic meter, closer together, their orbital velocities slightly compressed. The wave is moving outward through the ring at a speed determined by the ring's own surface density, propagating like a sound wave through a medium, except the medium is a disk of orbiting ice, and the wave moves at the speed set by gravity rather than pressure. You move through it, the density peaks, then it gradually thins again. The wave has probably been propagating through this region for millions of years. It will continue long after this particular particle beside you has drifted inward and been lost to Saturn's atmosphere. The structure is larger than any individual component of it. That is worth holding on to. Let the orbit continue now. Let the particles drift around you at their slow relative velocities. You are inside the rings of Saturn. You are moving at 20 kilometers per second, perfectly balanced between falling towards Saturn and flying away from it, in an orbit that the physics will maintain for as long as nothing disturbs it. Everything here is in motion, and everything here is still. The orbit has not changed. The particles around you are still drifting at their few centimeters per second relative velocity, so slow that if you reached out a hand, the nearest fragment of ice would take nearly a minute to close the last meter between you. The light is still that same low, golden late afternoon scatter, bouncing between surfaces in every direction. Saturn is somewhere below the ring plane, its enormous amber and cream-banded atmosphere occupying a vast fraction of the sky beneath you, visible through the gaps between particles when you look downward. Saturn from inside the rings is not the Saturn of photographs. From Earth, from Cassini's wide-angle cameras, Saturn appears as a luminous sphere hanging in darkness, with the rings as a flat disk extending symmetrically from its equator. From where you are, inside the rings, just above Saturn's equatorial plane, the geometry is completely different. Saturn does not appear as a globe, it appears as a curved horizon. You are so close to the equatorial plane that the curvature of Saturn's disk fills the view below you, not as a circle, but as a horizon that arcs from left to right, with the planet's banded cloud structure running in parallel bands across that arc. The clouds themselves are vast, the individual weather bands visible in Saturn's atmosphere, the alternating light zones and dark belts that give the planet its striped appearance, are each thousands of kilometers wide. The boundary between a bright zone and a dark belt, seen from this distance, is a gradual transition of color rather than a sharp line. The zones are lighter because they are higher in the atmosphere, rising convective cells where ammonia ice clouds form. The belts are darker, slightly lower, where material descends and the clouds are thinner. In the northern hemisphere, there is a feature not visible from Earth without a telescope, the hexagonal polar storm, a persistent hexagonal cloud structure approximately 30,000 kilometers across, larger than two Earths placed side by side, centered on Saturn's north pole, with winds around its perimeter moving at approximately 320 kilometers per hour. The hexagonal shape arises from a standing wave in the jet stream that encircles the pole, a pattern first observed by Voyager in the 1980s and confirmed by Cassini to have persisted for at least several decades. Its geometric regularity, a six-sided polygon stable across decades of observation in a turbulent atmosphere, is one of the more genuinely strange things in the solar system. You cannot see it from here, but it is there, and the planet whose rings you are orbiting inside is that planet, that enormous, strange, ringed world with its hexagonal storm and its 140-plus moons and its rings that span the distance to Earth's moon. There is something worth imagining about what it means to look at Saturn from this position and understand what you are seeing. Every observer who has ever looked at Saturn through a telescope, from Galileo in 1610 to a child at an amateur astronomy event tonight, has seen the same thing from the outside: a sphere, a disk, a gap, a glow. Even the Cassini spacecraft spent most of its 13 years photographing Saturn from orbit, outside the rings. The images it returned are extraordinary, some of the most beautiful photographs ever taken in the history of space exploration. The backlit shot of Saturn taken in September 2006, when Cassini positioned itself in Saturn's shadow and looked back toward the distant sun, showing the full ring system glowing in the scattered light, with Earth visible as a pale blue dot 1.4 billion kilometers away. That image has been called one of the most humbling photographs ever made. But no camera was ever inside the rings when it took that picture. No instrument has ever measured what you are measuring right now from inside the reflective medium. The ice beside you has never been photographed from this close. It has drifted in this orbit for perhaps 50 million years without being observed at all. Long before the first telescope existed, long before the first human eyes looked at the night sky with curiosity about what the bright, slow-moving points of light might actually be, this fragment of water ice was already here, already tumbling slowly, already catching and releasing the same low golden light. It was here before we were here to understand it. That thought does not require a response. It only requires a moment. Consider what it would mean to simply stay here. Not as a scientific instrument, not as a mission with objectives and downlink schedules and trajectory corrections, just as a presence inside the ring, moving with the ice at 20 kilometers per second in the direction of Saturn's rotation, completing one orbit every 12 hours. In 12 hours, you would return to approximately this position. The particle beside you would return with you. The density wave you passed through earlier would have moved outward a few tens of kilometers in that time, continuing its slow propagation. The hexagonal storm would have rotated several degrees. Mimas would have completed just over half an orbit. Nothing would have changed in any way that mattered. And in 12 hours, another orbit, and another, each one returning you to the golden scatter of light, the amber curve of Saturn's horizon below, the stars barely visible through the ice above. You could orbit here for a very long time before anything happened. That is what the ring particles do. That is all they do. And it turns out that doing one thing perfectly without interruption for 100 million years is its own kind of extraordinary. The Cassini division lies approximately 40,000 kilometers outward from your current position in the B ring. This is the most prominent gap in Saturn's ring system, a dark region approximately 4,800 kilometers wide that separates the B ring from the A ring. It appears dark from Earth because the particle density is much lower there than in the main rings. The reduction in particle density is maintained by a gravitational resonance with Mimas. A particle in the Cassini division would orbit Saturn in exactly half the time that Mimas takes, meaning it receives regular gravitational perturbations that prevent stable orbits from accumulating there. The Cassini division was observed by Giovanni Cassini in 1675, using a telescope crude by modern standards, but sufficient to resolve the gap from Earth. The spacecraft named after him spent 13 years in orbit around Saturn between 2004 and 2017, passing through the Cassini division multiple times, collecting particle data, measuring the magnetic field, imaging the ring structure at resolutions no Earth-based telescope could approach. The Cassini mission's final act was deliberate. Rather than leave the spacecraft in orbit where it might eventually collide with a ring or a moon and contaminate them, mission controllers directed it into Saturn's atmosphere on September 15, 2017. In its final hours, it transmitted data continuously, measuring the composition of Saturn's upper atmosphere directly for the first time. Then the signal ended. The spacecraft, which had traveled 7.9 billion kilometers to reach Saturn and had spent 13 years returning data that fundamentally changed the understanding of the Saturn system, became part of the planet it had studied. The data it returned is still being published. Papers using Cassini measurements appear in scientific journals every year. The mission ended. The knowledge it produced did not. In the ring material surrounding you right now, in the particle composition data, in the density wave measurements, in the structure of the ring edges, Cassini's fingerprints are everywhere. What you understand about this place comes from that spacecraft, from the people who built it, and from the decades of analysis that followed. The F ring lies approximately 3,000 kilometers beyond the outer edge of the A ring. You will not travel there tonight. It is far outward from your current position, but it deserves description because it is among the most dynamically active structures in the ring system. The F ring is narrow, only a few hundred kilometers wide, and it is continuously disturbed by two small shepherd moons, Prometheus and Pandora, which orbit just inside and just outside it, respectively. Prometheus, the inner shepherd, is approximately 86 kilometers across. Its irregular, elongated shape gives it a gravitational influence that is not perfectly uniform. On each orbit, when Prometheus passes closest to the F ring, it gravitationally pulls strands of ring material outward, creating channels, clumps, and braided structures visible in Cassini images as intricate, continuously changing configurations of particle streams. The F ring does not look like the main rings. It is a dynamic, evolving structure, braided, knotted, pulled into streamers and then reformed, a ring that changes visibly between Cassini images taken hours apart. The shepherd moon dynamic, moons controlling ring edges through their gravity, is the same mechanism at a small scale that explains the sharp outer edge of the B ring where you entered. The rings and the moons are not separate systems. They are one continuous dynamical system linked by gravity, continuously exchanging orbital energy and angular momentum. You are now drifting through a region of the B ring where the particle density is somewhat lower, a local minimum in the ring's radial density profile. The spacing between nearby particles has increased. You can see farther in every direction. The ring stretches outward from you in an unbroken plane to the limit of visibility. But you can see upward. Above the ring plane, the particles thin rapidly over a few hundred meters. The ring is vertically thin. Right now, in this lower density region, the ring here is thin enough that the faintest hint of the sky above is visible through the particle layer, not bright, not clear, but present. Stars, filtered and dimmed by the remaining ice particles above, register as faint points of light. This is one of the stranger experiences available in the solar system, standing at the interior of a disk that is simultaneously enormous in 2 dimensions and nearly nothing in the third. You are at approximately 100,000 kilometers from Saturn's center. At this distance, the orbital period is approximately 12 hours. You complete one full orbit around Saturn every 12 hours, half a day. The entire ring plane rotates with you, all the particles at similar distances following similar orbits, all of them at slightly different velocities because orbital velocity decreases with distance. Particles slightly closer to Saturn orbit slightly faster. Particles slightly farther orbit slightly slower. This differential rotation is what gives the rings their behavior. It is why they are a disk rather than a cloud, why collisions between adjacent particles are gentle rather than violent, why the density waves propagate at the speeds they do. The differential rotation also shears any large structure. If a clump of particles forms, pulled together by their mutual gravity, the differential rotation stretches the clump into a streak along the orbital direction. Over time, the clump disperses back into the general ring population. The ring is in a continuous dynamic balance between aggregation and dispersal. When you move outward from the B ring into the A ring, later in tonight's journey, you will pass through a region where this balance tips temporarily toward aggregation. Propeller structures, moonlets only a few hundred meters across, too small to be individually imaged by Cassini, but large enough to carve characteristic gaps in the surrounding ring material, exist throughout the A ring. Cassini tracked several of them for years, watching them drift slowly relative to the ring material. They are named informally after aviators: Blériot, Santos Dumont, Earhart, each one a few hundred meters across, embedded in a ring system that spans the distance between Earth and the Moon, slowly tumbling in the scatter of old sunlight. The ring does not know you are here. In, out. Let the orbit hold you for a moment without explanation. 20 kilometers per second, but nothing moves relative to you because everything nearby is in the same orbit. The physics of co-moving frames is what makes space travel feel, in imagination, like stillness. You are not stationary, but relative to the ice beside you, relative to the ring in every direction, you are barely moving. This is the Saturn system right now, not in a photograph from 2004, not in a Voyager image from 1980. Right now, as the words reach you, the rings are there, Saturn is there, the hexagonal storm is rotating above the North Pole. Prometheus is pulling streamers from the F ring. The density waves are propagating through the B ring. The shepherd moons are holding the edges in place. It is all happening at this moment far beyond the orbit of Jupiter, in the cold outer reaches of the solar system where the sun is a bright star rather than a warm disk. Nothing about any of it requires your knowledge of it to continue. It simply continues. There is a moon above you. Not immediately above, not a few hundred kilometers, not a few thousand, but in orbital terms, close. Enceladus, one of Saturn's most extraordinary moons, orbits at approximately 238,000 kilometers from Saturn's center, roughly 130,000 kilometers outward from your current position in the B ring. It is a small moon by solar system standards, approximately 504 kilometers in diameter, roughly the width of the state of Arizona. It is covered entirely in water ice, giving it one of the highest albedos, surface reflectivities, of any body in the solar system. It reflects approximately 99% of the sunlight that reaches it, making it appear intensely bright against the darkness of space. Enceladus is not a geologically quiet moon. In 2005, the Cassini spacecraft flew through a plume of material erupting from the moon's south polar region and directly sampled its composition. The plume was found to contain water vapor, ice particles, sodium chloride, silica, molecular hydrogen, carbon dioxide, and complex organic molecules. The south polar region of Enceladus is marked by a set of 4 parallel fractures in the ice, informally called tiger stripes, each approximately 130 kilometers long and spaced roughly 35 kilometers apart. From these fractures, water erupts continuously into space at approximately 1,400 kilometers per hour, driven by tidal heating from Saturn's gravitational pull on the moon's interior. Beneath the ice shell of Enceladus, beneath a crust of frozen water perhaps 20 to 30 kilometers thick, there is a global subsurface ocean of liquid water, in direct contact with a rocky seafloor, with hydrothermal vents that produce the hydrogen and silica detected in the plume. The chemical conditions in that ocean are similar to the hydrothermal vent systems on Earth's ocean floor, where life exists without sunlight, sustained entirely by chemical energy from the rock. Enceladus may be one of the most compelling places in the solar system to search for life beyond Earth, and most of what is known about it came from a spacecraft that flew through its plume and tasted the ocean secondhand. The material that Enceladus ejects into space does not simply disappear. It enters Saturn's orbital environment and gradually spreads along the orbital path. Over time, this material has accumulated into what is known as the E-ring, Saturn's most diffuse and extended ring, with its peak density centered precisely on the orbit of Enceladus. The E-ring is continuously replenished by the ongoing eruptions. Without them, it would fade within a few thousand years. The E-ring is actively maintained by a moon that contains a liquid ocean. The ring system you are orbiting inside is connected to that ocean. The ice particles surrounding you in the B-ring are different material, ancient, long orbiting, with a history measured in tens of millions of years, but they exist in the same physical system, governed by the same gravitational architecture, shaped by the same collection of moons, whose orbits define the boundaries and gaps and resonance structures of every ring from D to E. There is a sound analogy that helps understand the resonance structure of the rings, even though space itself carries no sound. When a string on a musical instrument vibrates, it vibrates at a fundamental frequency determined by its length and tension, and at integer multiples of that frequency, harmonics, overtones. The string does not vibrate at random frequencies. The physics of the string selects the frequencies that are geometrically compatible with the boundary conditions at each end. All other vibrations cancel themselves out. The ring system is governed by a similar principle, but in 2 dimensions and driven by orbital mechanics rather than string tension. The moons of Saturn orbit at specific distances with specific periods. Any ring particle whose orbital period is a simple ratio, 1/2, 1/3, 2/3 of a moon's orbital period, will receive repeated gravitational kicks at the same orbital phase. Over millions of years, those repeated kicks either clear particles from that region, creating gaps, or amplify density waves that propagate through the ring, creating structure. The result is that the ring system, viewed at fine resolution, is not a smooth gradient. It is a structure with layers of organization at every scale, from the large gap between the A and B rings, to the thousands of ringlets within the B ring, to the density waves within individual ringlets. The organization is entirely gravitational. No molecule chose its orbit. No particle decided to join a density wave. The structure emerged from the interactions of physics over time without intention. This is what emergent complexity looks like in the solar system. Not designed, not random, organized by the patient, impersonal operation of gravity across millions of years. You are inside a structure that is simultaneously one of the simplest physical systems imaginable, orbiting particles governed by Newton's laws, and one of the most complex looking in the solar system. Let us move outward now, slowly, through the Cassini division. The transition from the B ring to the Cassini division is one of the sharpest boundaries in the solar system. On the B ring side, the particle density is high, hundreds of particles per cubic meter, each a centimeter to several meters across. On the Cassini division side, the density drops dramatically within a radial distance of less than a kilometer. If you were moving outward and crossed this boundary, the visual change would be immediate, from the golden multiply scattered light of the dense B ring to a much sparser field of particles with open darkness visible between them. The Cassini division is darker than the main rings when viewed from Earth because the particles here are less reflective. Their surfaces are more contaminated with non-ice material, carbon compounds and silicates that darken with radiation exposure. They are older in their surface character, more irradiated, less purely icy. But the Cassini division is not empty. It contains its own ringlet structure, at least 17 distinct narrow rings, separated by gaps. Even a structure that appears from Earth as a dark gap contains its own intricate organization when examined at closer range. From your position, drifting into the outer Cassini division, the main difference from the B ring is space. There is simply more space between particles here. The light is still scattered from the particles that are present, but the dominant impression is of openness. Saturn's disk is now more fully visible, with less obscuration from the particle layer. The banded atmosphere, the pale gold zones, the slightly darker belts, is clearer than it was from inside the dense B ring. And in the middle distance, a small bright point moves against the background of stars. Mimas? At approximately 185,000 kilometers from Saturn's center, about 80,000 kilometers below you, Mimas drifts in its orbit. It is small, 396 kilometers in diameter, roughly spherical, heavily cratered. Its most prominent feature is a crater called Herschel, approximately 130 kilometers in diameter, so large relative to Mimas that the impact that created it nearly shattered the moon entirely. Herschel gives Mimas a resemblance, from certain angles, to the Death Star of science fiction, a coincidence that has made it one of the more recognizable objects in the outer solar system. Mimas is the moon whose gravity wrote the boundary you entered, the sharp outer edge of the B ring, that abrupt wall of particle density you crossed on your way in. It exists because of this small cratered object moving through its orbit 80,000 kilometers below you. The repeated gravitational nudges accumulated over millions of years swept that boundary clean and held it there. You entered the ring through a door built by a moon you can see right now as a point of light. The A ring is ahead. Moving outward from the Cassini division, the particle density rises again as you enter the A ring. The A ring is the second brightest ring in the system, less massive than the B ring, but structurally rich. It contains some of the most clearly observed density waves in the ring system, waves driven by resonances with Janus and Epimetheus, a peculiar pair of co-orbital moons that share nearly the same orbital path and swap orbits every 4 years in a gravitational exchange that has no analog elsewhere in the solar system. The A ring also contains the Encke gap, a 320-kilometer wide gap maintained by the small moon Pan, which orbits within the gap itself. Pan is 28 kilometers in diameter and shaped like a flying saucer. Its equatorial ridge, built up from ring material, swept up over millions of years, gives it a flattened appearance, quite unlike the simple spherical shape you might expect of a small moon. Pan's gravity not only maintains the gap, but also generates spiral wakes, compressed density patterns that trail behind Pan on both sides, propagating outward through the A ring. You can see the Encke gap from here, a thin, dark band crossing the A ring, with Pan somewhere within it, too small to resolve but gravitationally visible in the structure of the ring around it. A moon 28 kilometers across is sculpting a gap in a ring system that spans the distance between Earth and the moon. The scale relationships in the Saturn system are not like anything in ordinary experience. Let those scale relationships settle. The Encke gap, Pan, the A ring, the Cassini division behind you, the B ring you came from, Saturn below, Enceladus above, erupting its ocean into space, Mimas drifting in its orbit, holding the boundary that let you in. All of it simultaneously, right now. The ring system has been changing. Not on human timescales, not in any way visible from year to year, or decade to decade, or even century to century, but on geological timescales. The rings are not static. The Cassini mission measured the rate at which ring material is being lost to Saturn, drawn inward by electromagnetic interactions between charged ring particles and Saturn's magnetic field, a process called ring rain. The measurements suggested that the rings are losing material at a rate of several thousand kilograms per second. At that rate, the rings could be entirely depleted within 100 to 300 million years. They may already have lost a significant fraction of their original mass. The bright, massive B ring may once have been even brighter, even denser. In 100 million years, there may be no rings. In 300 million years, almost certainly not. Saturn will still be there, its atmosphere banded in gold and cream, its hexagonal polar storm rotating, its 100+ moons orbiting in their complex resonant architecture. But the ring system may be gone, or reduced to a faint, barely visible remnant, maintained only by Enceladus's ongoing eruptions. We arrived during the rings. You are inside them tonight, at the moment in Saturn's history when they are still here, still vast, still scattering light from a sun that is 80 light minutes away. That is not a small thing. Let the orbit carry you now, without explanation for a moment. The particles drift. The ring extends. Saturn is below. The stars are above. Mimas is moving against the star field, somewhere above and outward. Enceladus is erupting its ocean into space, and the E-ring glows faintly in the low outer solar system light. You are inside one of the most beautiful structures in the solar system, and the orbit is holding you perfectly. The orbit has carried you through the B ring, through the Cassini division, into the A ring, and now you are drifting back, moving inward again along the long, slow arc of your orbit, back through the Cassini division, back toward the dense inner B ring where this began, not because anything has pushed you, not because the orbit requires it, simply because the orbit is an ellipse, and all ellipses return. There is something in that worth staying with for a moment. All orbits are closed curves. They return, not to an exact point. The precession of orbital paths means that no orbit is a perfect repeating ellipse, and over millions of years orbital paths drift and shift. But on any time scale smaller than geological, an orbit returns. The particle beside you that has been in its orbit for 100 million years has traveled the same path approximately 100 million times. 100 million returns to the same region of space. 100 million passes through the same scatter of golden light. It has never stopped. It has never been anywhere else. It has simply orbited. There is something about that continuity, the absolute unbroken continuity of an orbit in the absence of disturbance, that is very restful to understand, not because it is exciting, because it is not. It is simply the most stable state available to a particle in a gravitational field. It takes energy to disturb an orbit. In the absence of that energy, the orbit simply continues. The ring continues. You are passing back through the outer B ring now. The particle density is rising around you again as you move inward. The scatter of light intensifies. The particles crowd closer. The ring reasserts its presence in every direction. This is the inner B ring, the region closest to Saturn within the B ring proper, approximately 90,000 to 95,000 kilometers from Saturn's center. The particle density here is among the highest in the entire ring system. The ring is essentially optically opaque. No light passes through it vertically. From above or below the ring plane, this region would appear as a continuous bright band with no transparency. From inside it, the effect is immersive in a different way than the outer rings. The particles here are closely enough spaced that the multiple scattering of light creates an environment of ambient illumination, not bright but uniform, coming from every direction where a particle exists to scatter it. The shadows of individual particles overlap. The light that reaches you has bounced off many surfaces before arriving. It is soft, diffuse, the kind of light that comes not from a source, but from an environment. Saturn is below, but here in the dense inner B ring, the view downward is partially obscured by the particle layer. Saturn's atmosphere is visible as a warm amber glow filtered through the ice, not crisp, not fully resolved, but present as a color and a brightness, warming the downward view. Above you, through the ice, the stars are not visible at all in this region. You are completely enclosed by the ring. The ice is above you and below you, because the ring has finite thickness, and you are at its midplane, and in every horizontal direction to the limit of visibility. The light is the scatter of old sunlight bouncing between hundreds of billions of particles in every direction. Saturn glows warmly below. The stars are hidden. This is what the inside of the B ring feels like. This is where the ring is most fully itself. The history of Saturn's ring observations spans nearly 4 centuries. Galileo Galilei first observed Saturn through his telescope in 1610 and reported seeing what he described as Saturn having ears, 2 additional objects flanking the planet. He could not resolve the rings as rings because his telescope lacked sufficient resolution, and because by chance Saturn's rings were oriented nearly edge-on toward Earth at that time, making them appear as a nearly invisible thin line. He described the configuration in an anagram, a common practice of the time for scientists wishing to establish priority without revealing their discovery immediately. That translates roughly to, "I observed the highest planet to be triple-bodied." When he looked again 2 years later, the ears had vanished. Saturn's ring plane had crossed Earth's line of sight, and the rings were edge-on, effectively invisible. Galileo reportedly wrote that Saturn had swallowed its children, an allusion to the myth of Saturn devouring his offspring. He never understood what he had seen. The rings were correctly identified as a flat disk surrounding Saturn in 1659 by Christian Huygens using a better telescope. Huygens proposed that Saturn was surrounded by a thin, flat ring, nowhere touching, inclined to the ecliptic. He was correct in every particular. The same Huygens also discovered Titan, Saturn's largest moon in the same period. Giovanni Cassini, in 1675, identified the division that now bears his name, correctly reasoning that the dark gap was a real separation between two distinct ring components rather than a shadow. He also proposed that the rings were composed of small particles rather than being a solid structure, a hypothesis that was correct but would not be confirmed observationally for another 2 centuries. James Clerk Maxwell, in 1859, proved mathematically that a solid ring around Saturn would be mechanically unstable. It would break apart under the differential gravitational forces it would experience. He showed that the rings must be composed of many small, independently orbiting particles. This was confirmed observationally in 1895 by James Keeler, who measured the Doppler shift of light from different parts of the ring and showed that the inner ring particles orbited faster than the outer ones, exactly as would be expected for independently orbiting particles following Kepler's laws, and the opposite of what would be observed if the rings were rotating as a solid disk. From Galileo's confused description of Saturn's ears in 1610 to Cassini's direct sampling of ring particle composition in 2017 is 407 years of increasingly precise understanding of a structure that was always there, always orbiting, always scattering light, waiting for instruments good enough to read what it contained. The ring particles around you right now were orbiting in 1610 when Galileo looked through his telescope and did not understand what he was seeing. They were orbiting in 1675 when Cassini identified the gap. They were orbiting in 1859 when Maxwell proved mathematically that they had to be orbiting. They were orbiting in 1895 when Keeler confirmed it. They were orbiting in 2004 when the spacecraft arrived. They are orbiting tonight. They have never stopped. There is one more structure worth understanding before the pace of tonight's journey begins to slow. The rings of Saturn are not the only ring system in the solar system. All 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, have ring systems. But Saturn's rings are by far the most massive, most visible, and most complex. Jupiter's rings are thin, dark, and composed primarily of dust, microscopic particles derived mainly from micrometeorite impacts on Jupiter's inner moons. They were not discovered until 1979, when the Voyager 1 spacecraft captured images showing a faint ring structure that ground-based telescopes had never resolved. Jupiter's rings are essentially invisible from Earth. Uranus has a system of 13 known rings, narrow, dark, and tightly confined by shepherd moons. They were discovered in 1977 when astronomers observed Uranus passing in front of a star and noticed that the star briefly dimmed and brightened multiple times before and after the planet itself blocked it, the rings producing a series of dips in the star's brightness that revealed their presence indirectly. The rings of Uranus are dark. They reflect only about 2 to 3% of incident light, possibly because they are coated with carbon compounds or other dark organic material. Neptune's rings are even fainter than Uranus's. They contain denser arcs, regions of higher particle density that persist because of resonances with the moon Galatea. The arcs are unstable over longer timescales and may be in the process of dispersing. Saturn's rings are different from all of these. They are brighter, more massive, more structured, and more dynamic. They are the only ring system in the solar system where you would have anything like the experience you are having tonight, immersed in visible, light-scattering ice, with Saturn filling the lower sky and the ring extending to the limits of visibility in every horizontal direction. The solar system has ring systems, but Saturn is the one that has rings in the way tonight means when it uses that word. Now let the pace of these words begin to slow. Let each sentence carry a little more space. You are still inside the B ring. The particles are still drifting at their few centimeters per second relative to you. Saturn is still glowing warmly below. The light is still the soft, multiply-scattered glow of old sunlight bouncing between ice. The orbit continues. The ring continues. Nothing here requires anything from you. The ice surrounding you formed from water. Water is the most common solid material in the outer solar system, more common than rock at distances beyond the frost line, the boundary in the solar system, beyond which the temperature is low enough for water to remain solid indefinitely. The frost line lies at approximately 2.7 astronomical units from the Sun, between Mars and Jupiter. Everything beyond it formed in the presence of abundant water ice. The moons of the giant planets, the Kuiper Belt objects, the comets, all of them are substantially composed of water ice. The rings of Saturn are mostly water. The same molecule, H2O, that makes up Earth's oceans and polar ice caps, and the clouds that cross the sky, and the snow that falls in winter, and the frost on a window on a cold morning, that molecule is what surrounds you in a different physical state, at a different temperature, at a different distance from the Sun, but chemically identical. The water in Saturn's rings and the water you are made of were both produced in the same way, in the interiors of stars that lived and died before the Sun formed, synthesizing oxygen from helium through nuclear fusion, and then in the molecular clouds where that oxygen combined with hydrogen to form water molecules that eventually became part of the disk of material from which the solar system assembled. The water in the ring particle beside you and the water in your body share an origin, not metaphorically, literally, the same nucleosynthesis, the same molecular clouds, the same solar system formation process. Different paths since then. One ended up in a ring particle orbiting Saturn, one ended up in you, but the same origin. You are made of the same material as the ring. Let the sentences shorten now. Let the pauses lengthen. The orbit holds. The ring is still there. 100 million years of orbiting and still there. Saturn's rings span 280,000 kilometers. Their average thickness is less than 1 kilometer. They contain enough water ice to fill Earth's oceans several times over. They have been scattering golden light from a sun that is 80 light minutes away. They have been doing this since before the first dinosaurs walked on Earth. And they will be gone eventually. But not tonight. The particle beside you is still there, tumbling slowly, catching the light on its fractured face, moving at its centimeters per second relative to you, going nowhere different from where it has always been. It does not know it is temporary. It does not know it is beautiful. It simply orbits. Let the body settle now. Let the weight of being somewhere, of having traveled in imagination through one of the most extraordinary structures in the solar system, let that weight rest. You know this place now, not every detail, not every measurement, but the shape of it, the scale, the ice, the light, the resonances, the moons that hold the edges, the ocean beneath Enceladus, the gap that Galileo saw without understanding, the 4 centuries of people looking at this planet through increasingly precise instruments, each generation seeing more, each generation leaving the next a slightly clearer picture of what surrounds that warm amber disk in the outer solar system. The physics holds. The orbit holds. The ring continues. The solar system is very old. The sun has been burning for 4.6 billion years. Saturn has been orbiting for 4.6 billion years. The rings are younger, perhaps only 100 million years, a recent addition to a very old system. But old enough that no human was present at their formation. Old enough that they have always been there from the perspective of every human being who has ever lived. Let sleep come now. Let it come the way a ring particle settles into its orbit, not forced, not hurried, simply finding the path the physics already prepared and following it. Outward, steady, in a closed curve that always returns. Not fighting anything. Simply in the orbit. Simply following the physics. This has been Quiet Science at Bedtime. Everything you heard tonight is real. Saturn's rings are out there right now. If tonight helped you sleep or made the solar system feel a little larger and a little more peaceful, please subscribe to the channel, leave a like, and turn on notifications so you never miss an episode. This channel is still very new, and every subscriber genuinely matters to what this becomes. Thank you for spending tonight inside the rings of Saturn. Sleep well.